Woo! Happy Movember! Today we're talking about the photoelectric effect and why it's crazy and how it made people realize that maybe photons are actually particles. One more reason that Einstein is a genius, and we'll also talk about an experiment that verified what Einstein said about the particle-like nature of a photon. In the time of the late 1800s, people had discovered something called the photoelectric effect, when they take a battery and they hook it up to an ammeter and they just connect it to a vacuum tube with nothingness in between. At first you'd get no current, and then they found if they took a light bulb and they shined a bunch of light into this vacuum tube, then it would knock these electrons off one end and zing, they would fly to the positive end, and this ammeter here would suddenly show that you had a current. And all these people in the late 1800s were like, "Whoa, that's amazing," or "jolly good," or whatever they said. In the 1800s, they were impressed by this photoelectric effect of knocking electrons off of a cathode, and they'd zip across to an anode. Now Millikan, who was known as the king of designing cool experiments, wanted to know, if these electrons are being knocked off, how much energy does each one have? And he came up with a clever way to figure out how much energy those electrons had. He figured out that if you had no battery on here and you knock these electrons off, a few would still flow over to the other side and you'd get a current. But he said, well, what if I put a battery on here and I can adjust the voltage across this thing and I reverse the polarity so that these electrons have to go against the way that they're being pushed. They've got so much kinetic energy that they're going to go across to the negative side anyway. And what he found out was that he could keep cranking up the voltage until they didn't have enough kinetic energy to zip across to that negative anode that they didn't want to go to in the first place. And so what he found out was that the kinetic energy that those electrons had would eventually balance the electrical energy, or the potential energy, that they would have in this field. Because these electrons here, they do not like going over to this negative charge. It uses up all their energy. And so what they said was that the kinetic energy, 1/2 mv squared, this is mass of an electron, was equal to the charge on an electron and the voltage across this. And the amount of voltage that you had to crank it up to finally stop the electrons from making it was called V sub s, or what we call the stopping potential. That's an important term. What was kind of cool was once you graphed it, if you graphed the frequency of the light that you were shining in there versus the energy of those electrons flying off, then you got this straight line graph here. And what they called, if you went below a certain frequency, no electrons got knocked off. And so what they called this was the threshold frequency, or the cutoff frequency, because below that you got nothing. But as you went to higher frequencies, the electrons got more and more energy. Now, Einstein kind of built off of some work by this guy, Max Planck, because Planck had been saying that the energy of photons, or of waves, as he thought, when they came off of vibrating things, could follow this equation, where it was n, which is an integer, times this constant, which we're going to call Planck's constant, times a frequency. And really what this boils down to most usually is just that any photon can have an energy that's proportional to its frequency and then times that constant. So now enter Einstein. Einstein said that the current wave theory of light at the time didn't explain things correctly, because that explained that if you had waves of any frequency, that they thought if you just had a high enough intensity that even low frequency waves should be able to knock off electrons. If you just went more intense, then you'd get more energetic electrons. But this experiment, that's not what happened. What did happen was only when you could have any intensity of low frequency, you got nothing. But then once you got up to high enough frequencies, you started knocking off the electrons with increasing energy. And Einstein said, let's think of these things not as waves, but as photons. And a photon is like a packet of energy, like a bullet that you're going to fire at something almost. And so that if you have a low frequency bullet or photon or packet and it hits an atom, it's not going to have enough energy to knock the electrons off, no matter if you fire a bazillion of them. But then once you get a higher frequency, that's like a larger packet or bundle of energy, and then you can start knocking off the electrons with more energy as you get to higher and higher frequencies. And this was quite novel at the time. Now here's another graph that relates to the photoelectric effect, and what we're saying is that when those photons, those bundles of energy, come in and knock the electron out, not all of the energy turns into kinetic, because some of that energy is just needed to knock the electron off. Now what that is called is our work function. And what the work function is the minimum energy that it takes to knock an electron off. And so what we end up with is that, based on what Planck said, here's the energy of a photon. It's going to split up its energy when it knocks an electron off. Some of that energy goes to the work function. Any energy that's left over goes to the kinetic energy of the electron. If we then break this down a little bit, we can say that the work function is equal to the threshold frequency times Planck's constant. So if I substitute that in here for the work function, and for the kinetic energy, as we said last time, charge of an electron times the stopping potential, we get this. Now, what's kind of nice about this is we can rearrange this into a little bit nicer form of y equals mx plus b. And if I rearrange this to say energy is equal to hf plus, minus hf0. This work function, or hf0, is our constant, and it's going to be negative. That's why you see it below over here. The slope, you can probably guess, is going to be Planck's constant, and your y-axis you would probably use as your energy. Oh yeah, and this slope, by the way, of this line is Planck's constant, and Planck's constant, just so you remember, is given the IB data booklet, but 6.63 times 10 to the negative, I'll forget this one, negative 34th, the weird units of joule seconds.